Hello grade 11s and grade 12s. In today's video, we're going to be looking at electrostatics, electric fields. Remember to stay tuned throughout the whole video because as a teacher, I will be giving you teacher tips that will help you level up your marks. I set, moderate, and mark exam papers all the way up to matric, so I know what you need to avoid in order to get the best marks possible. Remember to subscribe for more videos like this one. Let's jump right in. Before we jump into electric fields, I just want to remind you as grade 11 and grade 12 learners, you need to check out the exam guidelines document. So this is the exam guidelines for grade 12s, but grade 11s, because you are taught the electrostatics topic in grade 11 and tested on it again in grade 12, this document applies to you as well. So this document is free for everybody to access, can be found on the internet, and it outlines everything that you need to know for a specific topic. So you can see here behind me, it outlines exactly what you need to know for electrostatics, the definitions, the formulas, the types of calculations you need to be able to do. And as you can see here behind me, these are the exam guidelines for electric field, which is obviously what we're going to be focusing on today. So this tells you exactly what you need to know for the electric field section. So before we jump into all of that, I do want to remind you that definitions are a very important part of grade 11 and grade 12 work. And in the electric field part of electrostatics, there are two definitions. There's electric field, which you can see is this definition over here. And then we have electric field at a point. Now, what makes this confusing is that these definitions are very, very similar. Electric field and electric field at a point. So you need to read carefully to make sure that you are answering the correct definition because the definitions do differ. So behind me over here, these are the definitions for electrostatics for grade 11 and grade 12. We've been through Coulomb's law already in a separate video, so check that out if you need to do a recap on Coulomb's law. Then these are the two definitions on electric fields. We've got electric field and electric field strength at a point, or just electric field at a point. So they don't actually have to even say strength. Electric field at a point and electric field. Different definitions. So grade 11s and grade 12s, what this means is if we ask you to define electric field at a point and you give me this definition, they will mark you wrong. You need to give the appropriate definition to match the correct term. So those go together and those go together. But we'll go through those definitions now. This is just a very quick recap. And these are the formulae. Now, in terms of electric field, we will be discussing these two over here. And in my experience as a teacher who sets, marks, and moderates papers, and I mean, I've been teaching for years now, I see that my students often confuse when to use these formulas. And actually, they also confuse when to use this formula versus this formula. Now, I will repeat this again in the video, but grade 11s and grade 12s, it is pretty scary, but this is the truth. If you use the incorrect formula in your paper, you run the risk of getting 0 for that question. So if it's a 5-mark question and they ask you to work out the net electric field and you write this formula and you use that formula, which is electrostatic force, you will get 0 out of 5. If they ask for the field, the net electric field, you need to apply this formula or potentially this formula depending on the question. So it is extremely important to watch this entire video and make sure you understand when to use which formula. I will be going through these formulas in more detail and explaining when to use which formula. But for now, let's jump into what is an electric field? What is it? How do we describe it? How do you draw these things? Now, an electric field is a region of space in which an electric charge experiences a force. So what that means is, if you look at this diagram that I have over here, we have a charged object, so that is that red thing over there, and it has a positive charge. Now, because we have a charged object, so it says that all charged objects have an electric field around themselves. So because that red thing, because that red sphere, because that red object is charged, it has a positive charge, it creates an electric field. And we can't visually see it, the electric field with our eyes, but it is there. And in this case, in this diagram, it's represented by these lines, these black lines. So this electric field exists around this charged sphere. And remember I said an electric field is a region of space in which a charged object experiences a force. So one charged object creates the field, and other charged objects that are placed within the field
experience that force. So what that means is, and I drew a little dot here in blue, this is a separate charged object. It is another charged object. And when it is placed within that field, it will experience a force. So it will either move that way or it will move that way. It experiences a force. It will accelerate. Okay. If I had to place another charged object, let's draw one over here. That's also another charged object. Let's pretend it has a positive charge. It will experience a force. It will move away from this plus thing over here. So because an electric field exists around a charged object, it will cause other charged objects to experience a force. And one thing that you need to know how to do is to draw electric field patterns. So back to the exam guidelines, you have to be able to describe an electric field, which I just did with you. An electric field is a region of space in which an electric charge experiences a force. And I will discuss this part now, the direction of the electric field. But you also need to be able to draw electric field lines. So you see it says here, draw electric field lines for a single point charge, 2-point charges, and a charged sphere. Okay, so let's go over how to draw that. But in order to draw it, I need to explain the direction of the electric field. So take a look at that diagram that I just showed you over here, this one over here. You can see that this is a positively charged object. This is a positively charged object that is creating the field that surrounds it. Take note of which way the arrows are pointing. So because this is a positive charge that is creating the field, these arrows are pointing away. If I had to draw a negatively charged object and the electric field created by a negatively charged object like this one right here above me, look at how the arrows are pointing towards the negative. So look over here, it is a positive sphere creating the electric field. The arrows are pointing away. If it is a negative sphere creating the electric field, the arrows are pointing towards. And the reason why this is the case is because of the definition of electric field. So if you read the definition, it is over here. It says that the direction of the electric field, there we go, the direction of the electric field at a point is the direction that a positive test charge would move if placed at that point. Now, that sounds very complicated, overly complicated, but basically what they're saying is pretend that you are placing a little positive charge in the field. We're just picking up a little random positive test charge, putting it in the field, and we are thinking, which way will this positive move? And the way that the positive will move, that is the direction of the electric field. So again, if we look at this example over here, because the charge sphere that is creating the field is a positive, this is a positive. If I have to place a test charge, so another charge, let's say it's this green one, and I'm putting it over here. And remember, this is the positive test charge. It's just another random charge. And they say that it's positive. Which way will the positive, green positive, want to move? Think about it. You know from the previous video that like charges repel. So if it's a positive and a positive, they will repel. If it is a positive and a negative, they will attract. So like charges, if they're both positive, they will repel. So this green test charge, we call it a test charge. This green test charge will want to move away from this red one because like charges repel. So if I had to put a little green positive test charge over here, remember it's positive, it'll move that way. If I want to put a green positive test charge over here, it'll want to move that way. Take note how it is wanting to move away from the red one. So that is why the arrows point outwards, they point away. So I want you to just remember that if we have a positive creating the field, the arrows will move away. Just like that. If we have a negative charge that creates the electric field, the arrows will move towards. And the reason why the arrows will move towards is because remember, if we place a positive test charge, positive, opposite charges attract. So this green will want to move towards the negative. The positive will want to move towards the negative. I hope that makes sense. And that is why these look like this. So electric field lines around a positive charge looks like this. Positive charge, arrows point away. negative charge, arrows point towards. And this is an example of drawing an electric field of a charged sphere. So you can see that charged sphere looks like this. This is a sphere. If they wanted the electric field lines around a point charge, we would draw the point charge like this. So it'll be the same thing, except instead of a round sphere, we will do a point charge and the arrows will point away like this and it'll point away. And we would still have to label this as being a positive. Okay. Generally, they ask you to draw the electric field lines around a sphere, and this is where you get your marks. You get a mark for labeling it correctly, so label that this is a positive. You get a mark for the shape, okay, which I'll explain now, and a mark for the arrows. In other words, are they pointing in the correct direction? You can get up to 3 marks for a diagram like this. 3 marks. Now, some things that you must not do when drawing a diagram like this is the following. When drawing your electric field lines, please make sure that they never cross each other. So what I mean by that is when you draw your electric field lines, please don't end up drawing something where they end up crossing each other. Electric field lines can never cross one another. And please also make sure that when you draw them and they touch the sphere, that they don't cross each other here at the base either. Please also make sure that you use a ruler so that they end up being straight, and make sure that you label your lines. We also don't want the electric field lines to cross into the middle of the sphere. So make sure that you draw them neatly. Basically, try and make sure that they look like this diagram over here or like my ones over here. So remember, these are electric field patterns around single spheres. But you also need to be able to draw me electric field patterns around 2 objects. So on the left over here, we have the electric field lines around 2 unlike point charges. Unlike as in one is positive and one is negative. Remember, the arrows point away from a positive. So look, away from the positive and towards the negative. So in towards the negative, away from the positive. And when we have unlike point charges, remember these fields attract one another. That's why these are attached to one another. So opposite charges, their fields must join up like that. If you have like point charges, remember a positive and a positive, so that is what's behind me currently, over here on the right. If you have 2 like charges, so a positive and a positive or a negative and a negative, they repel one another. So take a look at the field lines. Note how they repel one another. So they never touch one another. Just make sure, so take a close look at what I've done here. Make sure that your lines over here don't overlap. Mine is very, very close on that diagram. They cannot touch each other, the field lines. They cannot overlap. But if it's 2 like charges, their fields repel one another. And just take note of the direction. Because these are both positive, the arrows move away. Okay, so knowing how to draw these things, very, very, very important. And here is another slide over here that illustrates how to draw it and which way the direction should move. In this slide over here, I show you that in reality, or I explain that in reality, electric fields exist in 3 dimensions. Obviously, on paper, we draw it in 2 dimensions. Another important thing to understand is that electric fields are the weakest where the field lines are the furthest apart. So here you can see the field lines are the furthest apart over here on the diagram, as opposed to, say, for example, over here. So let's label this A and label this B. At which point, A or B, is the electric field the strongest? You will say A because the electric field lines are closer together. Okay, so the electric field strength will vary. So the closer the lines are, the closer the field lines, and the closer you are to the charged particle that's creating the field, the stronger your electric field. And the stronger your electric field, the stronger the force that exists on that particle. So what I mean is this charge is creating the field. If I had to put a positive test charge over here versus one over here, let's call this one X and let's call this one Y. Which one will experience a stronger force? You will tell me X. The reason why is because the field, electric field, is strongest over here because it's closest to the charge. The field lines are closer together. So the formula that we can use to help explain this is this formula, which we will discuss later. The stronger the electric field, which is where the field lines are closer, the stronger the electric field, the greater the force that exists on this particle. And the greater the force that exists on the particle, the greater the acceleration of that particle. Okay, so the force is not constant. The force can vary because the electric field varies, and because the force varies, the acceleration varies. I hope that that is making sense. So speaking about electric field or electric field strength takes us to this formula over here. So they can call it electric field or electric field strength. And the formula, like I just showed you, to calculate electric field or electric field strength is this formula. And just take note that E stands for electric field or electric field strength. It's measured in Newton per Coulomb. I will show you how we get that unit now. And you calculate it by taking the force divided by the charge. Now, as you should know, force is measured in Newton. Charge, that is charge, is measured in Coulomb. You see how we're dividing? We're saying force divided by charge. So we're saying Newton divided by Coulomb. Newton divided by Coulomb. You should know maths. If I take this Coulomb to the top of this fraction over here, remember it has an exponent of 1, power of 1. When we take that to the top, it becomes N dot, or Newton times Coulomb to the power of -1. And how we say this is Newton per Coulomb. That's how we say that unit. So that's where the unit for electric field comes from. That's the unit for E, Newton per Coulomb. And basically the definition for electric field or electric field strength at a point is the electrostatic force experienced per unit positive charge. So it's the force experienced per unit positive charge. It literally corresponds to the formula. Remember, it's a vector, which means it needs a direction. And what this formula basically allows me to calculate is, you can see that I place this little charge at a certain point within an electric field. So this object over here, let's say that it is a positive object. It doesn't really matter in this case, but let's say it's a positive object. It creates an electric field. Remember, the arrows will point away because it's a positive. Then I place another object or another charge within that field. So it's a second charge. It is placed within the field of the first charge. And what this formula, the formula I just showed you, what this formula allows me to calculate is either the electric field at that particular point, this exact particular point, or it allows me to calculate the force experienced by this charge at that particular point within the electric field. So if I know the electric field at that point, let's pretend I know what E is at that point. Let's pretend it's 10 Newton per Coulomb. And I know the charge of this thing. Let's pretend it's an electron. Negative 1.6 times 10 to the negative 19. Remember, the charge of an electron is a constant. Then I am able to calculate the force that this electron would experience at that particular point. Obviously, this can't be an electron. Let's say it's a proton because it's a positive, so then it would be positive 1.6. I did tell you it's a positive. If I had to take that proton and I had to move it further away, so let's pretend I had to move it all the way down here, then the electric field might not be 10 anymore. It's further away, so the electric field will be smaller. Let's pretend it's 2. Then I can calculate the force on that proton, this proton. It'll be smaller because the electric field is smaller. I hope that that makes sense. So we use this formula, this one over here, in order to either calculate the electric field at a particular point, and I can do that if I know the force on that charge, and I know the charge of the charged object, or it allows me to calculate the force if I know the electric field at that point, and then the charge of the object. So that is when I use that formula, and I will go over that again, but this is for example, this is 2 questions that you can get, for example. So it says calculate the force, so we're looking for F, experienced by an electron. So we know the charge. The charge of an electron is negative 1.6 times 10 to the negative 19 coulombs. That is a constant. It's given on your formula sheet. At a point in an electric field where the electric field strength is 3,000 Newton per coulomb to the left. So that is E. So they're looking for F. They give me the charge, or you should know the charge because it's an electron, and they give me the electric field strength. So this is the formula that you would apply. The one that I just showed you. Okay? Or they could say calculate the field strength or the electric field strength. They're looking for E. At a point in an electric field where a charged particle of negative 3 nanocoulombs, so that is the charge, negative 3 nanocoulombs, remember we need to convert that to coulombs, but we have charge, experiences a force. So I will be doing these questions in a separate video, so check out the links in the description, but I just want to show you this is when we would apply this formula that I just showed you. Okay, so either you're given a force, you're given a charge, and you want electric field, so that's example number 2, or you're given an electric field, you're given a charge, and they want the force. So we have discussed when to use this formula above here in the corner, but when do we then use this formula? This is a different formula. And this formula is used when we are calculating the electric field or the electric field strength created by a particular charge. And we want to know what that electric field or electric field strength is at a particular distance away from that charge. So quickly looking at that formula, E, once again, is electric field or electric field strength. And it is measured in Newton per coulomb as discussed previously. K is a constant, it's Coulomb's constant. This has been in the Coulomb's law video discussed, but it will always be 9 times 10 to the power of 9, and that's given to you on your formula sheet. Now, big Q over here, I want you to think of this as the big Q. It's the charge that creates the field. Okay, so I hope you can remember in the formula that we just spoke about, we spoke about there being a little baby charge, this one over here, that we place within a field. So that is baby Q, the charge that we place within something else's field. But big Q is different. Big Q is this thing over here. It's the charge that creates the field. They are different. So one charge is making the field, another charge is in the field and it's experiencing the field. So think of big Q as the charge that made the field. It's big, it made it. Little small q in the other formula, in this formula, is the charge that we place within the field and it is feeling or experiencing the field. So in the second formula that we're discussing now, this one over here, it's big Q, it is the charge or the particle or the charged object that creates the field. Okay, that creates the electric field. It's very important to know the difference between them. And then R. R is the distance away from big Q. And the distance is always measured in meters. And if it's not, you're going to have to convert. With that being said, the charge always needs to be measured in coulombs. If that's not the case, you need to convert. And just a quick recap on converting charge to coulombs. The conversions are given in this table above me over here. And please take note that the conversions are not given on your formula sheet. So charge is measured in coulombs. Sometimes they might give it to you in picocoulombs, nanocoulombs, microcoulombs, or millicoulombs. If that's the case, you need to convert. So for example, if they say 6 microcoulombs, you need to know micro, I need to convert to coulombs by timesing by 10 to the negative 6. So 6 times 10 to the negative 6. So you convert by multiplying it with whatever it says over here. Okay, cool. That is awesome. So let's just quickly recap the differences once more between the two formulas. Very, very important that you know the differences. The formula at the bottom over here, this is just a different way to write this formula. It may be given on your formula sheet like this, but if we just go back to the formula sheet that I showed you that you will be getting in your final exam, they give it like this. Okay, they give the formulas like that. So just be aware of how you see your formulas given to you in your textbooks or in your study guides. It should be given like this. E is equal to F over Q. It's basically the same thing as this. It's just rearranged. Let's just keep it as the formula as given on the formula sheet. For this formula, remember that Q, this Q over here, this is the charge that experiences the force. It is placed within someone else's electric field. Okay, so it's like when I had something that created the field, it's going to be very rough, so excuse. And then I put something else, like here, like an electron or a proton or any other charge. That little small charge is Q. It experiences the electric field of something else. Big Q is the charge that creates the electric field. So in this case of this diagram, big Q will be this one. It creates the field. And little q will be the one that is placed within the field. In both formulas, E is the same thing, electric field strength. I hope that that makes it clear. So how would you do this? Calculate the electric field, or they could say the electric field strength, at a distance of 30 centimeters away from sphere A. So we've got sphere A. It's a positively charged sphere. And remember, this thing, A, although they didn't show it over here, A creates an electric field. So they don't show it, but you should know that it creates an electric field that looks something like this. I hope you know which way the electric field would be going. It will be pointing away. It'll be pointing away because it's a positive. They say at distance X, 30 centimeters away from sphere A. So they take from the middle of sphere A and they measure 30 centimeters. That is X. We want to know what is the electric field at that point. So 30 centimeters away from the charged object A. And they tell me the charge of object A. Now, because we want the electric field at a particular distance away from a charged object that created the field, we use this formula. I hope it makes sense that we don't use this formula. Okay, because we have a charge that is creating an electric field. So we need to use this big Q over here. This formula we would use if I placed another charged particle within the field and I wanted to know the force on it or the electric field. So it's not that formula, it's this formula. So we want the electric field at a particular distance here away from A. A created the field. So Q or K, is 9 times 10 to the power of 9. It's a constant. It'll always be K. Q, they say, is 3 nanocoulombs. Remember, I just showed you the conversions. Nano, to convert, is times 10 to the negative 9. So 3 times 10 to the negative 9. And the distance, they want it at 30 centimeters away. Now remember, R must be in meters. How do you convert centimeters to meters? I hope you know that you divide it by 100. So it will be 0,3. And the formula says square, so please don't forget to square it. Very big teacher tip. Please, please, please don't forget. A lot of my students forget to square it, unfortunately. And I get 300. Remember, we're looking for E, which means that it's electric field. So the unit is Newton per Coulomb. And because they want electric field, remember we said electric field is a vector, which means it needs a direction. You can't just say 300 Newton per Coulomb. You need to give me a direction. And remember, according to the definition, the direction of an electric field is the direction that a positive test charge would move if placed at that point. So what that definition is telling me is if I had to put a positive test charge over here, which way would it move? If I had to put a positive test charge at this point here, which way would it move? Well, because this is a positive, the positive test charge, and A is a positive, this will move to the right. It will move away from sphere A. So you can say away from A, or you can say to the right, because in this diagram, it would be to the right. It would move that way. In other videos in this playlist, I will go over more detailed calculations for electric field strength, where we have to work out the net. So when I have multiple charges, and I hope that I see you in those videos in the future. Check out the links in the description box below for more videos and more playlists. I I hope to see you subscribed, and I will see you in the next video. Bye, everybody.